Hi, this is my video number 34. Video 34, yeah. For this series or this video, I'll talk on flux. Flux, F-L-U-X. Okay. So, what is flux? Flux is basically the volume of fluid crossing a surface per unit time. Okay. So, what is flux? Flux is a volume of fluid crossing S surface S, yeah, per unit time. So how do we evaluate this? So we evaluate this flux using, we have double integral over the surface S f dot n ds. Okay, so if you have let's say this is our surface, given as S, Z equal to fxy, say, okay, fxy, and then we know that for if surface Z is given as that, okay, I can write this as Z minus f x y equal to 0. If I give name to this as, let's say, G, so we have that surface. Then if we impose the operator del to G, so what we have, this is minus of fx minus of y and 1. Okay, so this del G with respect to this S is that normal. Okay, this is the del G. So if you want to find unit normal, yeah, and unit normal, which is unit normal to the surface at that particular point. This is normal to the surface at so this is normal with length not equal to 1, but this is unit normal with length equal to 1. Okay, so we know that for n, we know the normal is that del G over magnitude of the del G. So that gives you a normal. Alright, so I'll give you a formal definition. Flux for the vector field, flux for the vector field F, okay, crosses the surface S, where S is given as Z equal to f xy, is given as, we double integrate as f dot n ds. Okay, this is, we integrate as f dot, we have n is this, okay, and ds as I've shown in the previous video, this is the magnitude of G dx dy. So we have here n is the G over magnitude of del G dx dy. That you can cancel out. What left is only that. Okay, now let's see example how to find flux. Example, okay, so let's say we have our f is given as 3x, 3y, and z. Okay, and S is the surface given by Z equal to 4 minus x squared minus y. The Z on the first octant. Okay, so determine the flux F on the surface S. So which means, so what we want to do is we want to find, or we want to evaluate this F dot and ds. Alright, as we have shown earlier that this is equal to, we integrate over S f dot negative fx negative fy 1 dx dy. So the rest is just substitute everything, what is f, what is fx, what is fy, and 1. You need to identify what is f, the function or the surface f. Now if you look at the surface S here, z equal to 4 minus x squared minus y, we can sketch this, alright, so that when we do the integration, we can determine the limit of the integration much easier. Okay, so we can try to sketch those surface S. So this is in 3 dimensions, so we need x, y, z. Okay, so if you look at this, on x-axis, we have z and y is 0, so x is plus minus 2. So x plus minus 2, minus we can ignore because we consider only first octant here. So just take the positive value. So let's say x2 is here. Alright, and then y on y-axis, zx is 0, so y equal to 4. So y equal to 4, probably need a little longer here. This is 4. Alright, and then on z-axis, xy is 0, so z equal to 4 as well, so that's 4. Okay, then we consider on plane. Okay, first we consider on the axis, then we consider on plane. So we have 3 planes here, so you need to consider each of them. First, let's say consider on the xy plane. Okay, consider on xy plane. On xy plane, z is 0. So what you can see from that, z equal to 4 minus x squared minus y. Okay, on xy axis, z is 0. So what we have, y is equal to 4 minus x squared. So you know this is a curve, like a cup. Alright, so we have that curve is given as that. Okay, so this curve is defined by that equation. Okay, of course we have negative side because we have negative here, but negative side is the other side of our plane, so we don't want that, because what we want is only the first octant. Now if you look at on yz plane, x is 0, so we have z equal to 4 minus y, right? 4 minus y, which is a straight line with a negative slope crossing at 4 and 4. So we have a straight line there. Just connect those 2 points. that. Okay, just connect those two points. Now on xz plane, y is 0, xz plane y is 0, so we have 4 minus x squared. So again, it's a curve. 4 minus z is 4 minus x squared, so we have something like that. Is a curve. Again, it goes to the other side, but we don't consider that because we deal with the first octant. So if you can see this, so this part here, this is our surface. That's our surface. Okay, so this line here, this is z equal to 4 minus y. This line here, z equal to 4 minus x squared. 4 minus x squared. And normal to the surface, yeah, because unit normal to the surface, and this is our n, and n is a unit normal to the surface. Okay, so our surface, if I put this, maybe I give a name to each of these vertices. Let's say I call it B, A, B, C. So our surface is given as those surface ABC. Okay, now we need to evaluate or to identify what is our f from the given surface S, which is z equal to 4 minus x squared minus y. Alright, you may take this as a function of xy. Alright, we differentiate partial derivative with respect to x because del f, this is what? This is negative fx, fx, fy, fz. Okay, and n is given as, yeah, del is the del x. So we need this del f del x, del f del y, del f del z. So from there you can find del f del x, which is fx is given as minus 2x, fy is given as minus 1. Okay, so your n is given as a negative fx, negative fy, and 1. So this is negative fx is that, so we have 2x. Fy is a negative, so we got 1. Z is 1. So we have those. Okay, then what left is we need to do, look at this formula, f dot those things. Okay, so f dot those, our negative fx, negative fy, negative no, this is 1. This is our f is 3x, 3y, and z dot, that part is given by that 2x, 1, 1. Okay, so what we have, if you perform this, we have 6x. This is a dot product, so it gives you scalar. So we have x, 6x squared plus 3y plus z. Okay, all right, so your z is 4 minus x squared minus y. You just substitute. Now next we need to evaluate integrate s f dot negative fx, negative fy, 1 dx dy. So, and this from that calculation. Alright, we know that this is equal to 6x squared plus 3y plus z. Then we integrate over s dx dy. So what happened to this z? This z is given as, look at our surface, z is given as those things. So 4 minus x squared minus y. So therefore this is equal to, we integrate over s, 6x squared plus 3y plus our z is given by that, plus 4 minus x squared minus y dx dy or dy dx. Is depend on how do we choose limit of integration. So this, if you look at this surface, okay, now we want to choose the limit of integration. Consider this, we project on the xy plane, y on the xy plane, because if you look at here, this is dx dy, so must be on xy plane. So look at your diagram. So if you look at on z positive, so that surface will be projected on xy plane. So we have this. So basically this is our domain of integration. Alright, so how to choose this? So you look at this y, you can choose y from 0, that line, x as y is 0, so from that line to that curve. Okay, so you integrate this y from 0 to that curve. We have 4 minus x squared, and then now this is for x. Look at this, x from 0 to 2, so x from 0 to 2, and then put that everything there, 6x squared, so you have 5x squared plus 3y minus y, so plus 2y plus 4 now dy dx. Okay, so I think you should have no problem to evaluate this. You can do this, x from 0 to 2, integrate this with respect to y, so we have 5x squared y plus 2y squared over 2, so y squared plus 4y. Limit y from 0 to 4 minus x squared dx. Okay, so this is equal to x from 0 to 2. We substitute this limit for y, so we have 5x squared, our y is 4 minus x squared, plus y is 4 minus x squared plus 4y, 4 minus x squared, and y0 you got 0 dx. Okay, so I think you can evaluate this. You just proceed this. In my notes I have the solution is 896 over 15. Please check this. Please check. Okay, so we have done that. So if you look at the this integral that we dealt earlier, this s, f dot n ds. So if s, so we have this surface, we have that surface, okay, so in this example, so what we did is we project this surface on xy plane. So that's why we have our n is given as negative fx, negative fy, and 1. And here we have dx, dy. So this means we project on xy plane. Now, is it possible? What happens if we project that surface onto XZ plane. So what we have, if we project on the XZ plane, basically we don't have Y, so we have what? So that's so we can write Y equal to on the surface. I can write Y as a function of X and Z. Now I can write this as Y minus F XZ equal to 0, and then I can take this. Let's say this is a function G. Then if we find the del of G, so what we have, differentiate respect to X, so we have minus Fx, differentiate to Y, so you got 1, differentiate respect to Z, so we have F negative Fz. Okay, so therefore our double integral over S. Now let's say I put this notation, I use a subscript, let's say X Z, to show that we project the surface on XZ plane. This becomes F dot Fx 1 negative Fz d x dz. Okay, so this if we project on XZ plane. If you do this using the same with the same problem here, instead of we do the projection on XY plane, if you do the projection on XZ plane, you will get the same answer. I leave it to that part as an exercise to you. Exercise. Okay, as well as I want you to think about this. If you project instead of XY or XZ, now we project on, look at from X positive, you project on YZ plane. If you project on YZ plane, what happened to our N? What happened to this part here? So you get, this is 1, negative Fy, negative Fz. So I want you to write that properly, and also do that problem, but project on YZ plane. So I leave 2 exercises for you for that. Okay, so let me give you another example. Now is I think I stop here. I'll give an example in the next video. Okay, bye bye.